I was sitting over at the toilet scrolling through the Blender subreddit because one must have their phone as they poop. Either way, towards the top of the page, we had something pretty rare happen, and that is a puzzle. Here's the puzzle. I want you to imagine that you have a sphere, a cube, Suzanne, a transformer, a banana, any object that is blocked by two barriers represented by these kind of like red and white walls. The puzzle is, how can I show the object through the secondary wall, the top wall, that can kind of see through the first? In other words, the question is, how do we make a portal to kind of render through? And people are making answers, but they're kind of half-assed and bad, right? Like they're using view layers, they're using compositing. These are all kinds of cheats. We want a pure way that lets us render at the same speed, maybe uses some clever node logic, and that's what we're doing. So first of all, let me show you the answer, and then we'll talk about how you would have actually gotten this answer. So we have our implementation of a sphere, a barrier, and another barrier, and it is through this kind of blue portal or window that we want to see through. Well, if I hide this portal, you can see I've done a implementation of this. You can already kind of see that this transparent plane, which by the way is just a shader trick, it's actually all like a single plane, looks like it's floating above. I can make this with the math look like it's significantly higher than the plane, even getting to like crazy heights. This is actually the solution for it. If I reset my numbers and apply the plane, you can see that it is perfectly overlapping here. And basically the trick that I'm going to show you is we are going to create this mask that emulates the plane, but we're going to need some complicated math to do this because this isn't just like a square cutout, it's like hovering above. You can kind of tell. Let me make that more obvious. And this is called pixel depth or parallax mapping. Turns out this is a simple implementation of it, but that's what we're going to be doing. So let me show you how to do parallax mapping, basically, to solve this problem. You won't have an easy time finding any other way to do it in Blender natively without compositing or some kind of cheats. Okay, so we have a red sphere, simple material. Green sphere, basically the same material but green, and then a blue, and I meant planes when I said sphere, and a blue plane here. The question is, how do I make a window on the green plane? Well, we're going to start off by hiding this blue one, because technically we're not even going to have this into render. This is more so going to be reference for us to take the green plane and cut a hole in it. We're not going to do this with geometry, but we're going to do this with shading. Okay, well, a naive approach for this is you might use like texture coordinates. So let's use object coordinates. By the way, the reason this looks so weird on mine is because of the color management I have. If it looks weird, it's the color transform. It doesn't really matter. But if we take these object coordinates and separate them, we can get the X and Y component. And this is kind of like the naive approach, right? So I'm going to, well, let's say that we compare to the center with some thickness. So I'm just kind of creating a custom mask based on its coordinates. And I'm going to do the same thing here. And then I just multiply these together. Well, this creates a window. And you might think, okay, that's it, right? We have the red color. We're also going to have transparency that we can see through. We mix them together using this as the mask, and we've solved this. But the thing that makes this problem hard is the plane is above. It's not directly on it. So we can't actually just use a regular coordinate system that's stuck onto it. For this tutorial, by the way, let me keep it on Filmic so it's nice. We somehow need to calculate a coordinate system that is somehow above it, okay? And that is what I am going to show you how to do. So here's the idea. I want you to imagine, and notice that this effect depends on which angle I'm looking at it from, so you can imagine that the camera matters. I want you to imagine that the camera is over here. This is the direction that somebody is viewing from, and kind of shooting out rays to say which direction we're looking at, we need to determine which points on the green surface should be transparent. Well, it's kind of simple. We look at the points that are in the shadow that are underneath this plane, and we make those ones transparent. except that is going to change depending on the perspective. It's not a simple projection downwards. That's only if we're looking at it through the top view, like this. If we change the view, it becomes a bit more complicated. So here is what we're going to do. I want you to imagine that we have a ray going through a point on the blue. So in other words, this surface point over here, let me actually change the color to something a bit more visible. In other words, the surface point over here will become transparent because if I shoot the ray back to the camera, it's intersecting here, which means it should be in the window. Whereas if I had a point over here, I shoot it back, it doesn't intersect the blue. So either way, what we have to do is we have to determine if a surface point on the orange is passing through our blue. But we don't really have a coordinate system to do that. So here's the idea. If we can determine, so we have a camera going to the point, if we can kind of determine the direction and the distance between our surface point and this kind of like imaginary plane on top, then we can perform a calculation to check, is it within or not within the plane? The question is, how do we get this distance? Like, how do we know if it intersects? And even if it does, how far away is that happening? Well, this is where our vector math and our trigonometry comes in. So I want you to imagine that we are looking at a point like this. By the way you get that vector is in geometry. There's something called the incoming coordinate system. You can see it changes depending on where you're looking at it. So this is the incoming coordinate system. And what it does is it colors the plane based on, right now it's our view, but imagine it's the camera. It's looking at this array that leads from the camera to the point. Of course, if the camera changes, then the shading is going to change. So we know the vector that goes over here, and somehow we need to calculate this one that goes to its intersection point on the blue plane. Well, to do that, we know that the direction of this is opposite to where the camera is coming from, okay? So if I take vector math and I scale by -1, all of the sudden, what have I done here? Yeah, that's fine. And I scale by -1. Right now it's going to invert the colors because this is what we're viewing, but if I go back to the orange, if I scale by -1, it's going to invert to go back to the camera. But I need to know the length of this intersection. Well, to do that, I want you to imagine that there's kind of like a triangle going on over here. So the triangle is composed of our surface point, the point immediately above it on the plane, so kind of going one up on the z-axis, and the intersection point. With this triangle, can we use trigonometry to calculate this length? Well, if we have this angle, the angle between the normal up direction and this kind of like incoming vector, if we have this angle, then we can calculate this hypotenuse by using cosine, because we know that the height of this segment going directly upwards is 1. Why do I know it's 1? Because this plane is 1 unit above. It could be 2 if your plane is 2 units above, but for me it is 1. So in other words, this hypotenuse, remember the SOHCAHTOA, cosine of theta is equal to adjacent over hypotenuse. Well, if we rearrange this equation, we get that hypotenuse, again, that's the length towards the intersection point, is going to be equal to, let's think, it should be a divided by cosine theta. However, a is equal to 1. So we can say it's the inverse, well, not the inverse, it's the reciprocal of cosine of theta. In other words, if we can fetch this angle over here, then we're good to go. And it turns out that's quite simple. Remember, dot product. It's the perfect way to get the angle between two vectors. So let's try that. I'm going to take a vector math. I'm going to use a dot product. And what are the two vectors? Well, the first one, technically it's the normal vector, but for us, it's quite simple. It's 0, 0, 1. But you can make this dynamic by using normal coordinates over here. For us, it's 0, 0, 1. This is the first vector, and the second vector is the one pointing towards the camera, which is the scaling by -1 to reverse the direction. This dot product, in theory, will give us this angle in the form of cosine theta. However, the rule of the dot product formula is that is only going to be the case if our magnitudes of each vector we're comparing, this normal vector and this incoming vector, if each magnitude is 1. Now, I think by default they should be, but just in case, you can throw a normalize onto here. This makes it a length of 1, and of course the vector 0, 0, 1 that points 1 unit upwards has a length of 1 already. So you can think of this as giving us cosine of theta, okay? And in fact, this is quite nice because I said we need the angle so we can take the cosine of it. We already have the cosine of it from the equation for free. So if I take this and now take the reciprocal, remember, hypotenuse is equal to 1 over cosine theta. Well, now we know the length of where its potential intersection point is. Again, we don't know if it intersected, but this is the distance it would be to our intersection point, and that is going to be the vector going towards the camera, but only for this amount of distance. In other words, I take this incoming that we reversed, that goes towards the camera, and I scale it. I say, go that direction with the magnitude of that hypotenuse we just calculated, okay? So now we basically have the vector that goes from our surface point we care about to its potential intersection, okay? But now the question is, how do we know if it is intersecting within our plane? Like, this is where it would happen, but does it actually intersect? Well, it turns out this is quite simple. Again, if we have a surface point and we have a camera that leads to a point such like that, that's the intersection. Remember what we did before with kind of like the object coordinates, right? We had our object coordinates. We did some simple math to do this. Well, if we know how to create this kind of square mask using a coordinate system that is attached to this, well, what's the difference of having a plane above it, right? We just need to shift the coordinate system. That's it. So we can run the same calculation, but it's not for object coordinates. It is for our custom coordinates, okay? So in other words, I want this potential point to go back down towards our orange plane, since that's where we're doing our calculations. So I'm just going to project it back downwards. And this is literally exactly downwards, going down by 1 unit on the z-axis. It's almost as if we're saying this surface point is actually this one over here. So this is the actual point, but we're pretending that it's shifted over because the camera's moving and there's kind of a trick of perspective. We're doing the same calculation with the object coordinates, but with this manipulated system. So in other words, what I can do is we have this vector already. I want to move it back downwards, which you can either subtract by 1, or another way to do it is multiply by 1, 1, 0. Because now you're projecting it on the XY grid. 0 is multiplied, z is multiplied by 0, so it becomes 0. So now our vector becomes quite simple. Our vector becomes this one here, that again represents our initial shading point to our shading point that accounts for our perspective. And now we just need to replace this with object coordinates. Now, you can't just do that directly, and you'll see the issue in a second. If I do this directly, indeed, it kind of seems to do something, right? By the way, the reason this is so big is we're making a threshold for whether or not it's cut. That's quite big. Remember, our plane, dimensions 4 by 4, means it has a radius of 2 by 2. So I believe if I just bring this downwards a bit, you can see it's almost doing what we want. Let me make it even smaller just for comparison. It's almost doing what we want, but it's kind of like beneath the plane. You can almost imagine it's underneath instead of on top. So there's something going a bit wrong here. Well, remember, let me see if I can undo and get to my annotations. Remember, we have our new surface point, but we're kind of going to treat this like it's object coordinates, which again is this kind of XY coordinate system where for each shading point, we're comparing it to the origin. That's what object coordinates are. So now, instead of just saying, look at the vector, compared to the origin for each point, we now add this kind of like secondary component that shifts it. So what am I saying? I'm saying we take our projected coordinate and we add on object coordinates. So now we're getting this new vector that is kind of like the corrected object coordinates. Now we might still run into some issues here, but let's see what we got. There we go. You can see it's a bit bigger, obviously, but it is mapping onto it. Now why is it a bit bigger? Again, because the plane is 4x4, so it has a radius of 2. And the fact that you can't see it is actually perfect, because that means it's perfectly overlapping, and if I get rid of it, like that. Now, some questions you might think. One, what if the plane is bigger? Let me make it 50% bigger. So now it's 3x3. Well, in that case, to puncture a bigger hole, or it's 6x6, in that case, you just increase these radii proportionally. Okay? That's that problem solved. Now, what if the wall, the barrier, is a bit higher? So I'm moving it 2 units up. Well, remember, what we care about is our point and our hypotenuse to the intersection point relative to the camera. Well, we were assuming to calculate this hypotenuse, we were assuming this height of A is equal to 1, but now it's 3 units up, so it's equal to 3. So do we need to do this calculation again? No, just take 1, make it 3, and now they perfectly overlap, such that you can see there's kind of like this floating plane. So what this kind of boils down to is we're going to have a height. So I'm just going to rename this height over here. And assuming it's a square, of course, you can have this be a rectangle or any shape really. If you can calculate it for the object coordinates, then you can do it for this with the displacement. We have the height and we have the size, let's call it, of our square. So this is the size of our window. And then this is the height, where again, if the height is 0, it's perfectly here. By the way, you should be able to do negative, which isn't what we want here, but it does create this kind of like cool effect, just so you know. But I'm going to set this to 1 and 2 and set our dimensions to 2x2, or the radius. So it's 4x4. I know I'm being confusing. That and a height of 1, such that, in theory, these should perfectly overlap. In fact, I'm going to go back. I'm going to make it 6x6, let's say 2 units above, which we can easily correct for. 2 units above, 6x6, which means maybe instead of size, I'll call it like radius, since that's why I keep like multiplying and dividing by 2. But there you go. So again, remember, all that's happening is we have a plane that looks like it has depth, but it really doesn't. It really doesn't. And we're mixing the color orange with transparency just like that. You could have done anything. You could have, I don't know, you could have done something like this where it's a window, but now there's this happening. Or perhaps you could have done translucency, which kind of looks funky, but you can do that, I believe, if I make... I don't know that much about translucency, to be honest with you, but I guess that is what it would look like. Okay? You could also run a subsurf or whatever. The goal of this one was transparency. Okay? So there you go. That is the solution to the problem. By the way, I'm going to... This is a big deal. Let me put it on the big screen. By the way, I'm going to put this answer file that I cleaned up on my Patreon. If you want to pick it up, great. I mean, it's better that you understood this tutorial than picking it up. But what I want to say is Patreon is the place to get blend files kind of like this, but just kind of like solutions to problems and projects that I've made over the last 4 years. And I am the only one who works on this channel, so Patreon directly funds me, and in that sense, the channel. So lots of new patrons coming on board recently. Thank you. Get project files, early access to tutorials I made in the past. And yeah, sorry if I've been like out of focus slightly this entire tutorial. But there's your solution.